Hi, Matt. How are you?
Hello, good, thanks. How are you?
Good to see you.
Yes,
Yeah,
likewise. I
yeah. Thanks for
wish it was
joining
in
us.
person, but
Yeah, no, I hope
yes.
next time I'll be in person, but I appreciate that you are giving this talk online, nonetheless. Okay, so I think everybody is here. We're going to start. If you're ready, Matt. Yeah.
Sure, and
Okay.
it should be 45 minutes, right?
Yes, that's correct.
Okay, good.
Okay,
Yep.
great. Okay, so welcome everyone to the last talk of the afternoon, the first day. We're very happy today now to have Matthew Young from Utah State University, who is going to tell us about UQGL11 and U11 Chern-Simons theory. Matt, please.
Great. So, yes, thank you to Hisham and Urs for the invitation. I would have loved to have been there in person, but this time it wasn't possible. So, today I'm going to talk about, well, everything I'll talk about will be joint work with Nathan Gear. It's on the archive at this address. So just to start, maybe let me outline what I hope to convince you of during the talk. So the main mathematical result is that we give new examples of what are called relative modular tensor categories. I'll explain what that is as the talk goes on. But the thing to keep in mind is that these are some kind of non-semi-simple versions of the standard modular tensor categories. Okay, and the place that we'll get these examples from is it comes from the representation theory of the quantum group associated to the Lie superalgebra GL11. And so it's a relatively simple superalgebra. It's somehow a degenerate case of the simple families, but for our purposes, it's somehow quite nice. And the kind of physical message of the talk is that, well, there's a general machinery, which I'll explain, which extracts from a relative modular tensor category a non-semi-simple three-dimensional topological field theory. And we'll argue that these examples we give here, they actually recover some previously known relatively simple physical models, namely supergroup Chern-Simons theory with gauge group U11 or some closely related group. Okay, so those will be the punchlines of the talk. Okay, so just to, I think probably everyone here knows this, but let me just recall it since I want to refer back to it. So if we think about the standard case of Chern-Simons theory with compact gauge group, so as studied by Witten in the late 80s. So this is a three-dimensional quantum field theory. It's a gauge theory. It takes as input the following two pieces of data. So it takes in a gauge group G, which let's just assume is, say, like SU2 or compact simple simply connected. Okay, and the second piece of data is what's called the level. I'll call it K. In the settings of here, this level is just an integer. Okay, and there should be some non-degeneracy conditions on the integer. I can't allow 0 and so on. Okay, but so the input is the gauge group, which is a group, and then the level an integer. Okay, and from this, you formally get invariance of smooth-oriented three manifolds. So the invariant is supposed to be this quantity here, which is the partition function, so Z of M. And what you do is you integrate over the space of all connections for a principal G bundle over your manifold M up to gauge transformation. And you kind of take the average over the exponentiated Chern-Simons value at that connection. Okay, so Chern-Simons of A, this is a number, and I take the complex exponential of it. Okay, so this should be an invariant that depends on the gauge group and the level. Okay, so this formally, these are invariants of the three manifold because it doesn't depend on any additional structure on the three manifold. And similarly, there's interesting line operators in this theory. So these are the Wilson lines. So I'll denote them like so. So I pick a knot or a link, let's call it, well, let's say it's a knot. So I call it K. It's embedded in my three manifold. I pick a representation V of the group G, and then I can weight the previous partition function. I can weight the integrand by the holonomy of this knot, holonomy of the connection along the knot, where I take the trace in the representation V. Okay, so the holonomy along the knot, this is an element in the group, and then I take the trace in this representation V. That's a complex number, and then I include that in my integrand. And so formally, this is an invariant of colored links or colored knots. And Witten's original motivation was that when you take the three manifold to be S3, the group to be SU2, and the representation to be the fundamental representation, these invariants are or should be the Jones polynomial. It's a purely three-dimensional description of the Jones polynomial, specialized at a root of unity corresponding to the choice K. Okay, but I don't have equal signs here because as a mathematician, I don't actually know how to define the right-hand sides. Okay, so as a physical level of rigor, this is what the construction is, but mathematically, it's hard to prove theorems using these definitions. So one of the standard ways to try to make Chern-Simons theory into a mathematical theory is by Reshetikhin and Turayev. So Reshetikhin and Turayev, what they did is as follows. So they started with an input, which is a modular tensor category. Okay, so it's categorical data. So a modular tensor category, so it's let's say a category which is linear over the complex numbers, say. It's a ribbon category, which means it's a tensor category. It has a tensor product. And I have a bunch of coherences that tell me how to relate the tensor product of V and W with W and V for any two objects. And they satisfy some coherence conditions. So this is called the braiding. Okay, but maybe this braiding is not this kind of simple swap map. It's more complicated. Okay, but the other points I want to emphasize in this definition of modular tensor category is that the underlying category is required to be semi-simple, meaning either there's no non-trivial short exact sequences in this category, or said differently, every object in this category is a direct sum of simple objects. Okay, so there's no non-trivial extensions. The category is also required to be finite in the sense that up to isomorphism, there's only finitely many simple objects. Moreover, the category is required to have the property that when I look at the quantum dimension of simple objects, these are all non-zero. Okay, and the final condition is that, well, there should be some non-degeneracy of this category. This is the modularity condition, which won't appear explicitly in the talk, so I don't discuss it here. Okay, but this, I mean, in words, this is the non-degeneracy of the S matrix. And the theorem of Reshetikhin and Turayev is that from a modular tensor category C, they construct a three-dimensional oriented, more or less, topological quantum field theory, which I'll call Z sub C. Okay, so Z sub C, this is a functor from the three-dimensional Bordism category, let's say, to complex vector spaces. And like I said, there's a little lie here. This theory might not be completely oriented, but it's close enough. Okay, but in particular, what does the data of this TQFT encode? Well, it encodes for every closed oriented surface, a finite dimensional complex vector space. This is the state space of the theory. And it encodes a complex number for each closed oriented three manifold. This should be the partition function of the theory, evaluated on that three manifold. Okay. So to connect, so this is a kind of general construction that takes in arbitrary modular tensor category. So the connection with Chern-Simons theory comes from particular examples. So this is work of Reshetikhin, Turayev, Anderson, and a number of others. So a large class of examples of modular tensor categories is constructed as follows. So you start with G, which is a simple complex Lie algebra, which I should think of as the complexification of the Lie algebra in my Chern-Simons theory. Okay, so I have a complex simple Lie algebra, and then I have an integer k. Again, there's some non-degeneracy conditions. Okay, and what Reshetikin-Traev and Anderson prove is that if you look at the corresponding quantum group specialized at the primitive kth root of unity, well, this gives you a tensor category. Okay, but this category, it doesn't have any of the required properties. It doesn't have many of the required properties of being a modular tensor category. So for example, this category, it has infinitely many simple objects. It has non-trivial extensions, and somehow most of the simple objects have quantum dimension 0. So it fails the first 3 conditions here. It also certainly fails the last one. Okay, but it turns out that in this example, there's a way to truncate it. I mean, somehow you throw away most of the category. This is the process of semi-simplification. And this semi-simplification, it fixes all of these problems at once. Okay, so we won't need what semi-simplification is, but formally what you do is you just set all of the modules who have quantum dimension 0, you just set those modules to 0. Okay, and it looks like that's only going to fix this problem, but for whatever reason, it fixes all of the problems at once. Okay, but from the point of view of this talk, the thing I want to emphasize is this category is quite large and interesting, and we throw away a lot of it to get this modular tensor category. Okay, and then the statement is that if you plug in this modular tensor category into the Reshetikin-Traev construction, the output 3D TFT is a mathematical model for Chern-Simons theory with gauge group, the simply connected Lie group that is attached to G, and at a level, I call it K bar, which is closely related to K. Okay, so this is it's basically accepted as fact now. From the point of view of this talk, I just want to emphasize that we don't have an a priori definition of Chern-Simons theory. And so the way to kind of argue that this TFT models Chern-Simons theory is, for example, to compute lots of things using Reshetikin-Traev theory and compare them to things in the physics literature. If they match, then it's reasonable to call this a model. So from the physical point of view, what is this modular tensor category C? Well, it's the category of labels for the Wilson operators in the Chern-Simons theory. Okay, so we should think that this category C is some kind of truncation of the representations of the group G. These were the possible labels of the knots in Witten's construction. And there's a physical reason why somehow most of the representations give 0 for the knot invariant. That's kind of the analog of this semi-simplification from the physics perspective. Okay, so the goal then, I mean, for today is to explain some analog of the statement that this modular tensor category models Chern-Simons theory in the case of a simple supergroup. Not a simple supergroup, but basic example of a supergroup. Okay, so the mathematical context of work is what I'm going to call Renormalized Reshetikin-Traev theory. So this is due to a number of authors: Costantino Gear, Patro Moran, Traev, Blanchet, Dorenzi. So there's a number of authors that contributed. I'll try to point them out as we go along. Yeah, but renormalized here means that I'm going to drop these assumptions of being semi-simple, finite, and having non-zero quantum dimension for simples and replace them with something weaker. Okay, so it drops all of these assumptions. Okay, so there's a kind of long history now of trying to do non-semi-simple quantum invariance, so kind of already 30 years of this or so. But I would say during the 1990s and early 2000s, most of these constructions were ad hoc in the sense that they were direct constructions maybe of quantum invariance for links or quantum invariance of three manifolds, some three manifolds, they have some functoriality and so on. Okay, so this includes like the ADO invariance, Kuberberg invariance, Henning's invariance of three manifolds, and then Keller-Lukashenko's partial 3D TFTs from non-semi-simple versions of modular tensor categories. But the framework I'm going to work in is this, I'll call it CGPT, so Cosentino, Gear, Petro, Turayev. So they have I would say kind of a full generalization of Reshetik and Turayev theory in this non-semi-simple setting. Okay, and this generalization, it recovers each of these kind of previous ad hoc constructions as special cases. So I'm just going to work in this framework. Okay, and like I said, their renormalized theory, it takes in ribbon categories which need not be finite, need not be semi-simple, and can have simples with vanishing quantum dimension. Okay, and so in particular, they spit out a 3D TFT of some sort. And this TFT is known to have kind of properties that are different than Reshetik and Turayev theories. So for example, it's easy in this renormalized theory to classify homotopy types of lens spaces. This is something ordinary Reshetik and Turayev theory has problems with. Similarly, this renormalized theory, it has a chance to produce faithful representations of mapping class groups of surfaces. Okay, again, Reshetik and Turayev theory doesn't do this. Okay, so what is this theory? And in particular, what's the kind of input category that we're taking here? Okay, so this is the notion of a relative modular category. Okay, so it's the following data. So again, I start with a ribbon category. So I have my category, I have a tensor product, I have the coherences between the tensors of two objects in different orders. Okay, and I give the following additional data. So first of all, I require that there's a direct sum decomposition of this category into full subcategories, which are labeled by the elements of some abelian group. Okay, so G here is an abelian group. I have a subcategory, C sub G. This is a full subcategory. Every object in C is a direct sum of objects in each of these homogeneous pieces, and there's no non-trivial morphisms between the various pieces. Okay, so, and I don't make any assumptions on this group. So it's abelian, but it doesn't need to be finite. Okay, so next I give a second abelian group, I call it Z. Okay, and I require that I have the data of a monoidal action of Z on this category. Okay, so I can think of this as follows. And sorry, I should have said, in this decomposition, I require it to be compatible with the monoidal structure. Okay, so if I tensor things in two homogeneous degrees, the result lands in the sum of their degrees. The dual negates degrees and so on. So in particular, if I look at the subcategory labeled by the identity, this is going to be a monoidal or even ribbon subcategory. Okay, and so I can ask for a monoidal action. So I think of this group here, it's a monoidal category where the objects are labeled by the group. Okay, and I give a monoidal functor from Z into this degree 0 subcategory. Okay, and I can think of this as an action of Z on the whole category because I can just tensor things in the category by elements of C0, but C0 doesn't change the degree, so it's kind of a homogeneous action on the entire category. Okay, but again, I don't require this group to be finite. Okay, and the last piece of data is what's called a modified trace. This is a key piece of information, but somehow I won't talk about it so much in the talk. So modified trace, this is the thing that's going to allow to talk about, in particular, modified quantum dimensions of objects. Okay, and part of the conditions of a modified trace is that if I look at the modified quantum dimension of a projective in my category, this is not zero. And so it's not true that every simple will still have zero or non-zero quantum dimension, but the projectives do at least. Okay, so this is the data. So I have a grading of my category. I have an action on my category of an abelian group, and I have this notion of modified quantum dimension. Okay, and this data needs to satisfy a number of conditions, which is going to weaken these finiteness, semi-simplicity, and non-zero quantum dimension conditions. Okay, so the first condition is that somehow most of these homogeneous subcategories are actually semi-simple. Okay, and for the purposes of today, this finite, or this group G, will always be infinite. And this subset X of the bad degrees where these subcategories aren't semi-simple, these will be finite. So for the purpose of today, that's what I mean by small. Okay, almost all of these subcategories are semi-simple. Okay, so this is the weakening of the semi-simple condition. The next condition is that, again, if I look at these homogeneous subcategories and I restrict attention to the semi-simple ones, then I require, well, I have this action of Z on this category. Can I require that up to the action of Z, this subcategory has only finitely many simple objects? Okay, but because Z can be an infinite group, it definitely doesn't mean that this subcategory has finitely many simples. It's just finitely many Z orbits of simples. Okay, and the final condition is this non-degeneracy. This is what's replacing modularity in the renormalized theory. So, but we have these kind of standard diagrams here. So here, this is the modified quantum dimension of a simple. So this simple VI, it's in one of these semi-simple categories. So the simples are projective. This modified quantum dimension is non-zero, so this is a non-zero number. Okay, and then I just look at this corresponds to one of the Kirby moves in the usual Reshetikhin theory. Okay, there's some more conditions, but these are the main ones that I need for the talk today. Okay, so this is the input data, and so the theorem. So this is due to Blanchet, Costantino, Gear, Paturo, and these first authors, they prove this theorem in a particular case coming from a certain quantum group for SL2, and Lorenzi proved the general categorical statement. Okay, but it's a direct generalization of the Reshetikhin triad theorem. So it says that a relative modular tensor category, from this data, we can build a what's called three-dimensional decorated TFT. Okay, so that's what I write here. Okay, so let me explain this a little bit. So the target here, instead of having just complex vector spaces, I now have complex vector spaces that are also graded by this abelian group Z. So remember, Z is this group that's somehow controlling the failure of finiteness of the category. And so I'm going to spit out vector spaces graded by this group. Okay, what is this cobordism category? So this is some modification of the previous cobordism category. So objects are surfaces, morphisms are compact bordisms between surfaces. So what does this decoration mean? So that's the decoration here is the same as the decoration by this category here. Okay, so what it means is that this TQFT, it's not quite a TQFT in the sense of a T as Siegel. Okay, but instead, it's going to produce invariants of what I'll call decorated surfaces. Okay, so this is a closed oriented surface sigma. And I also have the data of a cohomology class on the surface with values in the abelian group G, which is grading my category. Okay, so that's an additional piece of data, it's a decoration of the surface. Okay, but I can take, I'm allowed to take this cohomology class to be 0, for example. Okay, in which case I just get a surface in the standard sense. Okay, the more complicated statement is that the morphisms in this category, they're not arbitrary three-dimensional Bordisms, but they're only admissible Bordisms. So let me just say what that means in the case when the Bordism is closed, so the incoming and outgoing surfaces are empty. So this is admissible three-manifold. Okay, so this is the data. It's a compact-oriented three-manifold M. I have a ribbon graph T. This ribbon graph is colored, so each of the edges is colored by a object of my category. Okay, and again, I have a degree 1 cohomology class, which now is on the complement of this ribbon graph. Okay, so in particular, I have my ribbon graph, so it looks, I don't know, something like this. Okay, I have this cohomology class on the complement, so I can take the holonomy of this cohomology class omega around the meridian. So if I look at the holonomy of this meridian, this is some element in this grading group G, and I have the requirement that I color this ribbon graph compatibly with these holonomies, meaning, so this edge here of this ribbon graph, it's colored by some object, it should lie in this degree. Okay, so that's what I mean by a C-colored ribbon graph. Okay, and so what are the admissibility conditions? Again, I can't look at all such objects or tuples here, so it needs to be admissible. So the first condition is that, well, one of the ways it can be admissible rather, is that this ribbon graph can have at least one color which is a projective object of the category. Okay, so the other possibility is that this curve, the cohomology class could be generic. And by generic, I mean that there's some closed curve, gamma, in my three-manifold, such that when I evaluate this cohomology class on that curve, I get one of these generic grading elements. Okay, so this is what it means to be admissible. And so in particular, this TFT, it doesn't give invariance of all three manifolds. For example, if I take the three-sphere with no ribbon graph in it, I'm not going to get an invariant from this. Okay, so that's one thing to notice. So it does have a slightly different flavor than the usual Atiyah-Siegel TFTs. Okay, so in the interest of time, I'm skip that part. Okay, so now I can phrase the question that Nathan and I wanted to try to understand. So the question is there a physical realization of these 3D decorated TFTs? Meaning, for example, can we find some nice examples of relative modular tensor categories where this 3D TFT, it spits out something which looks like a physical model which we've seen before? Okay, so again, just to connect back to the original Chern-Simons setting, if this category C is the modular tensor category coming from representations of a quantum group, the answer to this would be compact Chern-Simons theory. Okay, so we'd like some kind of similar answer in this relative or renormalized setting. Okay, so some hints as to kind of what type of physical theory could give this is there's maybe two things to keep in mind. So the first is that somehow most examples of, or things we would want to be examples of topological field theories arise from the topological twist construction for supersymmetric quantum field theories. So examples of this construction are, like, for example, Chern-Simons theory with gauge supergroup. So I don't have a Lie group, but I now have a supergroup. These arise as topological twists of this Guyota-Witten theory, basically. Another example, which I personally got me interested in this, was if you look at the Rosansky-Witten theory of a holomorphic symplectic manifold, which morally, somehow this theory is supposed to be a purely fermionic analog of compact Chern-Simons theory. Okay, it has kind of many formal similarities to this, but from a mathematical point of view, somehow we don't, well, there's been not so much progress in defining this thing as a TFT. This is starting to change though. Okay, but the point is that when you construct a topological field theory from this topological twist construction, the output is usually, say, in 3 dimensions, spitting out categories of line operators, which are either DG categories or derived categories. Okay, and in particular, they're usually non-semisimple. Okay, so this topological twist construction is a natural place to look for categories of line operators, which are somehow much more complicated than the usual modular tensor categories. Okay, so that's one place to look. And the second thing I want to note, so we have all this extra data in a relative modular category. So the grading by this group, a monoidal action by a different group. So one place to look for this is that if your quantum field theory has a global symmetry, which is some group G, okay, then you expect to be able to couple that theory to background flat connections for this symmetry group. Okay, so what this means is that, for example, if I'm looking at line operators in a theory with a global symmetry group G, what I can do is I can say, for example, I have my 3-manifold M, I have a background flat G connection. Okay, and what I can do is now look at analogs of line operators. Sometimes they're called like non-genuine or extended line operators, which are present somehow in the case when I have this flat bundle, which has holonomy the element G around the knot that I'm defining these line operators on. Okay, so I don't know. So if I have a knot here, say inside my manifold M, I can look at the holonomy of this connection around a meridian of the knot. That's going to be an element of the group G. Okay, and I can look for line operators that are defined in this context. So such line operators, they should form a subcategory called C sub G, and all of the extended or and this larger class of line operators, this would be my category C. Okay, so inside here, I have this subcategory C sub 0. This is where I take the trivial line bundle L. This would be the kind of just standard line operators that are defined without any background flat connection. Okay, but if so, in particular, for trying to realize the TFT with a relative modular tensor category, which is graded by G, it's natural to look at TFTs which have that as a symmetry group. Okay, so there's a number of examples where some things are known about realizing these TFTs. So the best studied example is coming from what's called the unrolled quantum group of the Lie algebra SL2. So I'll talk about unrolling in a minute, so I don't want to talk about it in this case. So Blanchet, or BCGP, they in particular prove that this category of modules for this unrolled quantum group, it's an example of one of these relative modular tensor categories. And they do many computations for the resulting TFT. And so the TFT is relatively well understood, I would say. Okay, so trying to connect to physics, there's a number of different authors who have studied different aspects of this. Kreutzig, Dimafte, Garner, and Gear. So they have the proposal that this TFT of BCGP, it's what's called the A-type topological twist of n equals 4 Chern-Simons theory with gauge group SU2 and matter. So, and so what they do is, so they knew the computations in this TFT. They then developed the computations in the physical quantum field theory to match it. Okay, so they had to do quite a bit of work in the physical setting to kind of get the computations to the level that matched BCGP. Okay, and the computations match. But at least to me, this quantum field theory is quite complicated. It would be, I mean, is this kind of SU2 is quite a simple Lie algebra. Does the physical construction need to be so complicated to realize it? Some other work, so Gukov, Sin, Nakajima, Park, Pace, Sopenko, they did computations in Rosansky-Witten theory that match various aspects of BCGP, and similarly Cosentino, Gukov, and Putrov. So they're studying these Z-hat invariants and relate them to various expansions of the BCGP invariants. Okay, so for SL2, I would say this is kind of the proposal, and there's quite a bit of evidence for it. These ones are studying kind of slightly different aspects of the question, but are closely related. And so today, in the last part, I'm going to talk about GL11. So GL11, at the moment, well, before Nathan and my work, there was no real proposal for what this TFT should be modeling, but it doesn't mean that there was no work on kind of quantum topology of GL11. So there's a number of authors that had worked on that. So we're certainly not the first people to think about how GL11 fits into the world of quantum topology. Okay, so in the last, so I have a bit more than 5 minutes, so let me try to, so maybe just let me recall. So the Lie superalgebra GL11, this is just endomorphisms of the complex supervector space that has even dimension 1 and odd dimension 1. Okay, so it has this, it's generated by a central element, the identity, this element G, which is somehow like a grading operator. And then I have the upper or the kind of lowering and raising operators. So these guys here, these are odd because they swap the parity, and these parts here are even. Okay. So the unrolled quantum group for this Lie algebra, it's defined as follows. So it looks quite like the quantum group you would define, okay, but it has a couple differences. Okay, so I've labeled the elements E, G, X, and Y. They're corresponding to the E, G, X, and Y in the classical case. Okay, and I have a new element, an invertible element K, which morally we should think the logarithm of K is E. Okay, this is the kind of unrolling part of the quantum group. Okay, and well, we have these relations which are kind of the standard way that you would quantize the classical relations. Okay, and so this is a quantum group, but it's a quantum super algebra. It has a natural Hopf algebra structure, so it's categories of modules. Is a tensor category. It's kind of possible as an input to this relative modular story. Okay, so since I'm a bit late on time, I'm not going to talk about what the modules look like. So let me state Nathan and my theory, and let me kind of state what our proposal for the physical theory is. Okay, so what Nathan and I proved is that, so you have this category dq, int, let's just ignore the int part. Okay, so q here, this is the parameter in the quantum group. Okay, and dq, this is the category of all modules for this unrolled quantum group. Okay, but it depends on this parameter q. Okay, and what Nathan and I proved is that there's kind of these categories, they break up into two different types. So the first type is if I don't put any conditions on Q. It could be root of unity, it could be generic Q, whatever. Okay, so for this choice of Q, each of these categories, they admit a relative modular structure. Okay, so, but somehow these relative modular structures, they're somehow uniform in this parameter Q. Okay, it's one class of relative modular categories. Okay, the second class is that when Q is a primitive root of unity, these categories, they admit a different kind of relative modular structure, meaning their gradings are different, the actions of this group Z are different, and so on. Okay, so again, so when Q is a primitive kth root of unity, I get there's a relative modular structure on this category. And let me just point out what does the data look like in these categories, this relative modular structure. So the grading group is C mod Z, which as a group, this is just C star, which means we're looking for physical theories that have C star global symmetry if we want to realize this. Okay, this group Z that controls the non-finiteness, it's an infinite discrete group. It's two copies of the integers and then a Z2 coming from the boson fermion grading. And this X, which is a subset of this grading group G, this is just consisting of two elements. So it's certainly small in that sense that I alluded to before. Okay, so this category, it's graded by C star, and only two of the subcategories are non-semisimple. So it's somehow mildly non-semisimple. Although those two subcategories that are non-semisimple are kind of terrible. So
Matt, are you there? He's
okay.
probably okay. You're back.
And so the proposal that Nathan and I have is that so what this slide didn't change.
You froze a little bit, but yeah, just go ahead. Sorry.
Okay, sorry. My internet was sending exclamation points at me. Okay, so the proposal of Nathan and I is that each of these relative modular categories, they give rise to they model a physical quantum field theory, which is somehow more familiar than these examples of Kreutzig-Diemoptic Garner gear. Okay, so what's the proposal? So the claim is that if Q, this quantum group parameter, is arbitrary, then what this TFT is modeling is what's called PSL1 Chern-Simons theory. So this has other names in the physics literature. It's basically the Rosansky-Witten theory of the cotangent bundle of C, or the B twist of the n=4 free hypermultiply. But I mean, to me, this was a little bit surprising. PSL11 is not very interesting. PSL11, this is just a fancy name for the two-dimensional, purely odd abelian Lie superalgebra. So that doesn't seem like a very interesting Lie supergroup. Well, somehow it isn't, but the physical theory is still interesting. Okay, and the second part of the proposal is that if K is a primitive, excuse me, if Q is a primitive kth root of unity, then the TFT, the physical quantum field theory we're modeling, is U11 Chern-Simons theory at that level. Okay, this has another name. It's basically the equivariant Rosansky-Witten theory of the cotangent bundle of C. Okay, so we should think this equivariance group here is somehow the bosonic part of U11. So to go from PSL11 to GL11, we need to add the bosonic part. That's this kind of equivariantization. Okay, so I'm basically out of time. So how do Nathan and I kind of provide evidence for these proposals? Well, we just do it in the same way that there's evidence that Chern-Simons theory for compact group is modeled by Reshid-Deacon-Sharaev theory. So many physicists have done lots of work on different aspects of U11 Chern-Simons theory or U11 Wess-Zumino-Witten theory. So in particular, Rosansky-Salur have a huge number of calculations. This was already in like 1991 to 93. So there's many calculations in here to compare answers to, at least. Mikhailov and Mikhailov-Witten, they studied supergroup Chern-Simons theories from the perspective of brane constructions. Okay, again, there's many results in there that we can try to compare to. And then there's some other groups that also computed things that we compared to. And so maybe just let me, instead of going through the final slide. So for example, Rozansky-Soler, they compute mapping class group actions, which Nathan and I match on the nose with the mapping class group actions we get from our renormalized Reshetikhin-Sharayev theories. Mikhailov and Mikhailov-Witten, they also compute mapping class group actions from like a geometric quantization point of view. They compute Verlinde formulas. They argue about global symmetry groups and so on. Okay, we're able to compute, I mean, we can't compute these things in the same way they compute them, but our computations match the end answers. Okay, so in particular, we get the same Verlinde formula from them. We actually get a stronger formula, which actually computes the dimensions of state spaces, which in this graded setting is strictly stronger than Verlinde formula. So there's a number of further calculations that we compute. We are able to match all of them. Well, basically anything in the physics literature we found, we were able to reproduce, and we were able to compute more than it seems has been computed in the physics literature. So, of course, we can't prove this proposal because we don't have an a priori mathematical definition of what these theories are, but if we take seriously the physical calculations, we're able to reproduce these. And so it's reasonable to call our mathematical TFTs models for these physical quantum field theories. Okay, I think I'll stop there.
Thank you, Matt. Any questions for Matt? Yeah. Okay.
Hi.
Hello.
Did I get it correctly that in your category, the fiber over the neutral element is, again, not semi-simple?
Correct. It's very non-semi-simple. It's terrible over the... Yep.
Do you have an understanding why this fiber, apparently in all models we know, wants to be non-semi-simple?
Well, I mean, somehow this fiber contains the trivial module, which is never going to be projective in a non-semi-simple module category, right? I mean, that's, in our case, that's why this subcategory has to be non-semi-simple. If I take is that the type of answer you would look for?
Well, the next question would be, there's a second fiber, if I get it correctly, in your case.
Yes.
Do you have an understanding for this fiber as well? Do you expect that there are always, that this is related to the centers, to elements in the center? Or, to me, it looks like a miracle, to be honest.
So, it's hard to say. I mean, I understand this example of GL11 where certainly it's related to the center, and for unrolled SL2 it's related to the center. But from the definition of relative modular tensor category, I don't know offhand, and I never tried to think about it really.
Okay, thank you.
In this example, certainly yes, but that's just because we can understand this example so explicitly.
Okay, that's very intriguing. Other questions for Matt? Okay, if not, let's thank Matt again for the very nice talk. Thank you, Matt.
Thank you.
And I appreciate that you gave this talk when apparently it's dark still there, right?
I mean, it would have been light 2 days ago. We changed time, so now it's just always dark.
Oh, I see. Yeah, that's right. Daylight savings time. Yeah, that's right. It was Sunday,
exactly,
right?
So.
Yeah.
Exactly. Yeah. So.
Okay. I appreciate it that we
Okay.
were
Thanks again.
this early. Thank you, Matt. Take care.